All right, section 1.2 is where we're going to encounter the first word that is directly related to calculus. It's also the first concept that we've encountered that you wouldn't have seen in pretty much any other calculus or any other math course. So the concept is the concept of limit. So we're going to work a lot in this section about conceptual ideas, understandings of what this actually means. So my definition that I'm giving you is a very loose definition. It's not really like precise. It's more of a general idea for the moment. A limit is really a y value that you approach, but you may or may not actually touch. Okay, so you may in fact arrive at the location, but you may also just get very, very close to the location, and that would be the limit value. Let me draw you sort of a couple of pictures of how that could look in a graphical sort of point of view. So if you had a curve that did something like this, and it was nice and smooth, and you didn't have to pick up your pencil to draw it, anything like that, and we talked about this particular point right here, and I need to put some axes in here, otherwise it doesn't even make any sense, so let me do that real quick. So this is the x value at this location, and this is the actual y value at that pink dot location, and that value right there is a value that's on my curve. It's a y value that I do in fact touch. So the limit, when we're talking about that, would actually be that particular y value. Now if we do this exact same picture, but instead at this location right here where I had that pink dot, instead we have an open circle. You've seen that happen before in math, right? Where you've got an open circle. On this particular graph, it's exactly the same as the one before, except that I don't actually touch that particular point. Okay? It's a y value you get very, 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 very close to, but I don't actually touch it. So that's sort of the discriminating factor between the may or may not touch it is that we have these sort of things that are holes that are allowed in this discussion. Okay? A couple of notational things that are really important as we are looking at this. These three notations we will see used quite a lot. The one at the bottom is the most prevalently used. But we're going to go down the list of this, and I'm going to talk to you about how this is sort of read. So on the very first one, LIM, we would say limit. So this is the limit of the function f of x. So the limit of f of x as x approaches, so that's that x and that arrow. The number is 3, it approaches 3, and then the positive means from the positive or the right-hand side of the graph. So if you think about your xy axis, of course this is the x-axis, and this is the positive side and this is the negative side, right? Positive side of x, negative side of x. So when we're talking about this little plus right here, we're talking about the positive side over here. Right, the positive side over here, or the right-hand side of the graph, okay? And then the same is true for the negative side. So if we're looking at the limit of f of x as x approaches 3 from the left, that would be from the negative side. So you see the little negative notation right here listed. And then if there isn't a plus or a minus after the 3, then we automatically mean that it has to approach from both directions. Now, my picture above doesn't really lend itself to having that be a different value, but you're about to see quickly an example where it does. Okay, so bear with me. I'm going to show you how this actually plays out with a concrete example next. But this is the notation. Okay, plus means from the right, negative means from the left, and no notation after the number means from both sides. All right, one more definition. Whoops, sorry. Before we actually move on to an example. Limit existence. We say that a limit exists if and only if the corresponding one-sided limits exist and are equal. So in other words, if in fact we have the limit of f of x as x approaches some number, and we'll call that number a just to keep it generalized, if that actually has a value, we'll say L. Okay, it has a value. So L and A here are just numbers. Any number you want to put in there really will be just fine. Okay, so if this has a value, this happens if, and I'm going to put a double F, if and only if, that's what IFF means, if and only if, like in here, the limit from the left So that's the limit as x approaches a from the left of our function equals the limit as x approaches a from the right of our function. And the picture I drew on the previous slide does that very same thing. Whether it was the filled-in pink dot or whether it was the open circle, both sides, both from the right-hand side and from the left-hand side, we were getting close to the same y value. So write that down, and I'll go back to your picture so I can show you what I mean visually by that description. Okay, does everybody have those details written in? Okay, so like on this picture, what we're doing is we're approaching this particular, I'll give it a different name since I've called it A over here. We'll call this A right here. If I'm approaching this particular x value, which is called A, then I'm going to be traveling along my curve. Those arrows are indicating the direction I'm traveling. That would be traveling from the left-hand side. This would be traveling from the right-hand side. And they both are approaching the same location in space, right? It's the same place. So this actually fits the description that's on the next page, the next slide that we just did already. The limit here exists because they both approach the same spot in space. Okay, so let's do an example, and so you can see where that doesn't always have to happen. So this is the picture that is drawn in your notes, at least fairly closely. And the directions tell us to identify each limit or state that it doesn't exist. So there's something different about this picture than the last picture that I was drawing. Generally speaking, what's different? It looks like it's in two pieces, right? They aren't both lines in this particular case, but they are different two pieces of the graph, okay? And I saw someone else going something like this. Is that what you're doing? There's like a jump or a gap on the graph. Do you guys see that too? So both of those features are an interesting piece of information that's going to sort of come about in what we're looking at. All right, so the first example, or the part A of this example says it wants us to find the limit as x approaches -1. So -1 is this location right here. That's the x value, -1. And the first thing it tells us is plus, so from the right-hand side. So we need to be on the right-hand side of x equals -1. So on the graph itself, we're over here somewhere, and I don't even care where you start. It doesn't make any difference. So pick a spot on the curve, and you're going to start there, okay? So I will pick this location on my curve to start at for no particular reason whatsoever. Let me use a different color today. All right, so I'm going to start in that location. And what this is telling me is that I want to approach, that is, get close to an x value of -1, which means I'm already on the right-hand side of it, but I need to be moving toward x equals -1, which means I'm moving like this. Everybody with me? But I'm not going to jump over x equals -1. I'm just getting close to x equals -1. So I'm slowing down, I'm arriving at my destination kind of thing as I get close to that sort of opened hole in the graph. So the question this is actually asking us then is, what y value am I getting close to as I get very, very, very near to that x value, -1? What is the y value I'm getting close to? 2. So that's the limit. The limit is 2. Okay? This location right here has a y value of 2, and that is exactly where I'm getting close to. All right, the next one says that I want to get close to the same x value, but I want to do it from the negative side. So I have to start out on the negative side of the graph, something further over to the left than I am already at. Okay? Again, it doesn't matter where you start, just pick a spot. So I'm going to pick this spot right here. And I still need to be approaching or getting close to the x value, -1. So this time, as I'm traveling, I actually am traveling toward that dot, right? That closed-in, filled-in dot. I'm not going to get anywhere near the open circle at all because that's not on the part of the graph that I'm on right now. So as I am moving along the curve, and in this case it's actually a horizontal line, but as I'm moving along that line, what y value am I getting close to? It's 1, and I'm actually at the y value of 1, aren't I? Yeah. So actually, on the first case, I was actually getting close to it and didn't touch it. On the second case, I'm actually at it for quite some time because it was a horizontal line. And if I actually end up arriving at -1 flat out, I'm also still at y = 1. Okay. All right, so what this C is a comparison. C is saying I want to approach the value from both directions. Okay, so I want to come at this thing from both sides. Okay. Well, there's a problem. What's the problem? They're not the same, right? From one side I arrive at 2, and from the other side I arrive at 1, and 2 and 1 are not the same number. So when I have that happen and they don't actually meet, that's when we say that the limit does not exist. You can put D and E. You can write out does not exist. Does not exist could have two features. The feature that we're working with in the moment is this sort of a jump in the graph, this place where they don't meet up. The one-sided limits aren't the same. Okay, is everybody good with the first three? Okay, I'm going to erase some pieces of information from my picture. All right, the next one tells us we're approaching an x value of -2. So -2 would be right here. That's my x value of -2. And how am I doing it? From the right, from the left? I mean, what's going on? Both sides. Okay? Let's start out from the right because we started out from the right before. You can start anywhere you want on the right-hand side. So I'll start right here. And you're moving towards the x value of -2. Now, you do end up having this place in the graph where you have an open circle, but you're just going to keep moving left. So you're going to move right on down here. There's nothing wrong with that. Okay, so from the right-hand side, what do you approach? What y value? 1. I'm at a y value of 1 if I keep moving towards that x value of -2. Let's do it from the other side now. So let's start over on the left-hand side, the negative side. If I start over here and I move towards my x value of -2, what y value am I getting close to? 1. And it's the same, right? I did it from both sides, and yes, I had to jump across a little, piece of the graph. That's fine, because I can keep moving beyond the jump. Okay, that's the kicker. I can keep moving beyond the jump because I haven't gotten to the desired x value yet. So now that I'm at the same x value from both directions, they actually meet, right? They're approaching the same y value. So I'm at the same y value from both directions, and that y value you told me was 1. So the limit as x approaches -2 is actually 1. And I actually get there too. I mean, that is the value. Okay, any questions on that one? We kind of did D by rolling in parts A, B, and C all into 1, right? Because I didn't have an A and a B before it that had the one-sided limits. All right, we're going to do the same thing again. We're going to do it at x = 0. All right, so x = 0. Where is that on my graph? Yeah, middle meaning the y-axis, yeah. So this is x = 0. It's the y-axis, yeah? So if x is equal to 0, I'm not labeling that as a location, but maybe I should write it a little bit differently. I don't want that dot there either. All right, so this is -1, this is 0, this is 1. How's that? Is that clear? All right, so x is equal to 0 along the y-axis. And this doesn't, again, have a plus or a minus after it, so we're indicated that we're supposed to be doing it from both directions. So we'll start on the right-hand side. And if there's nothing special about that, that's just the pattern I was already doing. So we start on the right-hand side, and we move toward the x value of 0. And this one is not exact, so just approximate with me. What would you approximately say the y value we're getting close to is equal to? I think it's less than 3 because it's definitely not on the paper or on my screen crossing at this location, right? I'm definitely not crossing at this hash mark. So something slightly less than 3. Maybe you write 2.7, 2.75, 2.5, I don't care. But something between 2 and 3 should be your answer. So it's looking like it's getting close to about 2.7, I think is what we'll go with for me. And then we're going to do it from the left. So on the left-hand side, you can start anywhere you like on the left, and then you're going to move toward x = 0. Again, I have this sort of weird jump that I'm going to have to make, but I can certainly do that because I haven't gotten to x = 0 yet. So I just keep moving, make the jump I need to make. I mean, you know how to jump, right? You just move your feet, and you don't actually cross all the ground in the process. You're jumping. All right, and what happens? What y value are we getting close to? The x value is 0. Not the x. I want to know what y value are we getting close to. Still about 2.7. Whatever we called it before, it's still getting close to the same location because they're both getting close to this particular, well, it's the y-intercept is what it is, right? Getting close to that y-intercept. So, what is the limit as x approaches 0? 2.7. And of course, we're approximating the 2.7, which is fine. Any question on that? Okay. All right, we're going to take one more look at a calculator issue. And this actually is where we finally get it called what I was doing before. This is called a numerical process. Numerical just means to estimate something using numbers. So when you hear somebody talk about, there's a math class called numerical methods. It's using numbers, methods using numbers to do different approximations. So we're going to do a numerical process. Now this directions actually say to use numerical and graphical evidence, so we're going to do both things, and they both happen on your calculator anyway. And what we're going to do is we're going to conjecture. The word conjecture, you may or may not know what that word means. Conjecture means guess, like educated, well thought out, good guess. That's what it means. So you're guessing whether the limit exists, not random guessing though, okay? And if it does exist, then what does it appear to be? All right, so take a look then. This will be easier than the numerical stuff you were doing in the last section, so that's great news, right? So you guys are all well ahead of what you actually need to be able to do this particular problem. This says I want the limit as x approaches 3. Now, we've already talked about from the picture before that means we need to do it from the right-hand side and from the left-hand side moving toward 3. So think with me for a moment. I want a number slightly bigger than 3. What did we do in the last section that was slightly bigger than 3? 3.1. Very good. So I'm going to use 3.1. And then I want a number still slightly bigger, but closer to 3 than the one before. 3.01. And then what might the next one be? Yeah, 2 zeros in there, right? 3.001. We'll get to the calculator in just a second. Let's fill in the other column of x's. If this column is slightly bigger than 3, then the other column should be slightly smaller than 3. So what would be a value very close to 3 but slightly smaller? 2.9. Now we want to get closer to 3 than 2.9, so we could use 2.99. And finally, excellent news. All right, you've got all your x values, so let's take a look at the calculator now. All right, so just like last time, what we're going to do first is we're going to put the graph into y equals. You need to make sure that you're using the entire numerator as the numerator, so either with parentheses or with math type, depending on your calculator you're using. Mine requires me to put parentheses on top and on bottom in order to make sure it's giving it the correct information. And we're going to go into the table like we did before, which is second graph. And we want values for x in the table that are the ones we created for our columns on the paper. So you're going to use 3.1, 3.01, 3.001, and then 2.9, 2.99, and 2.999. And we're going to fill in the corresponding output, or the f of x values, from our table in the calculator. So I've got 6.1, 6.01, and 6.001. Then I've got 5.9, 5.99, and 5.999. And as we're looking at this table that we've just created and we're going down the table, this right here, I want you to be aware of what you're doing. This is taking the limit as x approaches 3 from the right, because these numbers are slightly bigger than 3 of our function. I'll call it f of x so that I don't have to write it all out. That is this piece here I'm calling f of x. Okay? So if I go down the first column, the 3.1, 3.01, and so forth, what is the left-hand limit? I'm sorry, the right-hand limit. I said the wrong thing. 6, right? I mean, I'm getting closer and closer to the value of 6. And if I do the second table, and I'm looking at the limit, this is actually the limit from the left because the numbers are slightly smaller than the number 3, right? They're a little bit less than. Of my function, I'll still call f of x. And what's that limit?
6.
That's also 6. Now, because those two are equal, we can say, or we can conjecture, that's what we're actually doing, guess, educated guess, that the limit of our function as x approaches 3 is, in fact, the number 6. So this is the numerical evidence that conjectures this. It's just two tables, one from the left and one from the right, and we're comparing them. Is that okay? Now, we're going to do a graph. So we did a graph on the previous slide, but it was a graph where I had already drawn a picture in for you. We're going to use your calculator to do the graph for this one now. You've already got the equation in there. I'd like for us to make sure that our windows are all set the same. So either if you could hit window, or even better, let me just do a standard window, which you can hit zoom. And then the standard window is zoom 6. It's a good place to start if you don't have any reason to start anywhere else. The standard window is negative 10 to 10 on the y-axis, negative 10 to 10 on the x-axis. Okay? All right, so this actually looks an awful lot like a what? The graph. Looks like a line, right? All right, so the first thing I'm going to do is I'm going to draw this graph in here. It looks like it's a line. Looks like it's crossing at about, what, 3-ish? So this is a sketch. And I'm saying that it looks like it's crossing at about 3 here. Ballpark, something like that. Might even slide it up just a little bit because it looks a little bit funny. We'll go with that. Now, if I'm wanting to find the limit as x approaches 3, which is what it said, then that means that I want the x value of 3. So that's down here. So the blue value that I've got on my screen, it doesn't look blue to you guys, but the one on the x-axis down here, this 3, is the one that I'm concerned about because that's the one they told me about, x equals 3. X approaches 3. So in fact, the location that I'm looking at is this location right here on the curve. Right? And the question is, what's going on in that location? So it does in fact appear that we're going to be approaching from both sides the same value, right? I mean, whatever it is, it looks like it exists. It doesn't look like a jump in the graph or anything like that. And you can use your calculator to trace over that value. So if you hit just the trace button, my trace is now here starting at x equals 0, y equals 3. You can start then this 0, and if you trace, this x value will increase. And you want your x value to get close to x equals 3. So that's 2.978 right now. Okay, that's the x value I'm currently at on my screen. And my y value is at 5.978. It's awfully close to 6, right? So it does seem reasonable. If I go one little bit higher, I'm at 3.19. That's actually quite a bit over, but that's how far it got me. And then I'm at 6.19. 6 seems like a reasonable answer. Okay? If you weren't sure, like if you didn't believe that, or if it jumped too far to give you confidence in that fact, you could zoom in. So if I hit zoom and I select number 2, and then I hit enter, it zooms in on the piece of the graph. Now you don't see the axes anymore, which might feel a little bit unhelpful, but you still see the x and y values down here at the bottom. So you can still maneuver in that window, and you just move your x till it's a little bit more comfortable for you to see. Look, here's 2.97, and there's that 6.12. Here's 3.01, and I'm at 6.19. So I am very close. Oh, I'm sorry, I didn't hit trace. I'm sorry, it's my fault. Trace, let me try that again. All right, there we go. 2.97, I'm at 5.978, and at 3.03, I'm at 6.03. I mean, that's fairly convincing argument anyway. It gives me a good feeling of being able to say, yep, I think this is it. Sound good? All right. Now, yes. Is your calculator doing something funny?
Yeah.
Okay, let me take a look.
It's still
It's in modes in rating. First of all, it needs to be in ratings. Okay, I think you're in polar mode, but I didn't see it do that. Do you have anything saved in here right now?
What? No.
Anything said. Let me reset it afterwards, and it should fix it. Okay, so just remind me once we get done with this part of it, and we'll fix it. All right, we're going to do one more example, very, very similar to this. Tell me, example 3. What's the only difference between example 2 that we just did and example 3 that we're about to do? Plus on the top, right? It's the only thing that differs. So changing it in your calculator, easy peasy, right? All we're going to do is we're going to change the expression in our y equals so that the equation has a plus sign in it right there. Okay, we don't even have to enter the data in the table again. It's the same table data that we did before because we're still using the same x approaching 3. So this is still 3.1, 3.01, and 3.001. I still have 2.9, 2.99, and 2.999. And now I have very different output values. So I have 186.1. I have 1806.01. I have 18,006.001. On the other side, I have negative 174.1, negative 1,794.01, and negative 17,994.001. And I'm going to write that same notation, and I expect to see that you write the notation on these as well, like I'm showing you. This is the limit. X is approaching 3 from the right of your function f of x. Okay? As you go down this table, what appears to be happening from the right-hand side? Yeah, it looks like it's getting infinitely large. Every time it looks like I've increased the number of digits, right? And not just the number of numbers that are there, but like the size of the numbers that are there. I went from hundreds to thousands. I'm now in tens of thousands. So this looks like it's approaching infinity. Okay, remember, we're just making a conjecture, so we're not proving that fact, but it's what it looks like. Let's do the left-hand side. The limit as x approaches 3 from the left. What happens as I go down this table from the left-hand side? Yeah, that looks like negative infinity, doesn't it? I mean, it's negative big, big, big values that I'm getting larger with every time. So what do you think we would need to say about the limit as we approach flat out 3, or 3 from both sides? It doesn't exist because they don't match, right? The limit does not exist. Let's do our standard window again. So I want you to hit zoom 6. Your calculator looks a little bit funny. You only even see values until you see this sort of vertical line. Yours may or may not have a vertical line depending on how new your calculator is. Some of them do a better job with dealing with that. I don't see anything over here. I can change that real quick. So if you hit your window button, and let's just change our Y max, that's how far our screen goes up. And let's make it go up to, we'll try 20 and see if that's enough. And then I'm going to hit graph again. It's going to change the scale of my window. You can see this now a little bit. I've got this curving feature down right here. I've got what appears to be a vertical line here. And then I've got another piece of the graph up here. Okay. Any guess as to what's happening where it looks like there's this vertical line? What is it?
Is it like an asymptote?
It's an asymptote. Now, it shouldn't really draw the vertical line in. Did anybody's calculator not draw it in? Yeah, you guys have newer calculators. The newer versions of the calculator can tolerate the asymptotes better. So those vertical lines, it shouldn't be there. It's really not part of the graph. What my calculator, and those of you who have an older operating system like I do, what it's trying to do is it's trying to connect things. Well, what do you do when you connect something that's not connectable? Well, it's really, really low up here and it's really, really high down there. We're just going to connect it with line. So that's what it's doing. All right, so if you take a look at this graph. It's going, as you move towards, the x value of 3, which is the vertical line you're seeing. As you move towards this, you eventually plummet down here. Right? That's what asymptotes do. You get really close to that line that you're not going to touch. And if you're on the right-hand side, you're going to trace along this curve this way, going up, right? And it's going to get infinitely large. So on your graph, you end up with... All right, so I'm going to draw it appropriately, and I would ask that you do that as well. You do need an asymptote line. You just need it dotted. because it doesn't really part of the graph per se. And it's at the value 3, so I'll go ahead and mark minus 3. And again, I don't have to draw this to scale. I'm just trying to get an image of what's happening. And the image of what's happening is something like this. So you can see as we approach it from the left-hand side, we get negative infinity. And from the right-hand side, we get positive infinity. Okay, so that it's in fact that verifies the numerical data that we were finding. Yes?
How do we know if the asymptote's there if like our calculator doesn't show it? Or do we have to add it?
Well, you're still seeing that feature. If we zoom out a little further, it'll probably be a little bit more obvious. I'm going to make my window without actually telling it to zoom out because that sometimes makes things a little bit funny. You can just make your y-axis a little bit bigger, so you can go, say, from negative 20 to, I'll go with 40. And it starts to look a little bit funny, but again, you can see that sort of decreasing feature. Even without the vertical line, you can see the features of it going through here and here. So you can zoom in and out. You can play with your window on your y until you're convinced of what's happening one way or another. Do you know why? Do you remember from college algebra or an algebra class you had? Why in the world this one ended up with an asymptote, number 3, and number 2 didn't? Both denominators actually equal 0. What's different, though? Factoring, yes. The numerator on number 2 actually factors. It factors into x minus 3 and x plus 3. And on number 2, when that factors, it actually has the ability that the x minus 3s would cancel, the numerator and the denominator, which would in fact create a hole in your graph. So you couldn't see it because your calculator doesn't show you a hole in the graph. But there was actually a hole in your graph right there. Okay? Whereas on the other problem, x squared plus 9 does not factor. It does not have the ability to reduce with the denominator, and hence we still have the asymptote in the graph. Okay? So we'll get to some more of that, and I think it's section 1.3. But I've done one more example. Number 4 is an example where your answer does not have to match somebody else's because there's multiple ways that this can be done. Now there's some features that have to be the same, namely the features that it gives you. It says you're going to sketch a graph of a function with the given properties. The first piece of information we're all going to draw exactly the same. It says f of 0 equals 1. What does that mean? Y is equal to 1, and what's x? 0. So that's like a point on our graph, right? So we've got the point x equals 0, y equals 1, which is a y-intercept right there. That should be on all of our graphs. These pieces of information, however, might be drawn differently, at least portions of them. This says that the limit as x approaches 0 from the left, okay, so from this side of the graph, I'm supposed to be getting close to a y value of what? 2. Well, a y value of 2 would be right here. So I'm supposed to be getting close to that from the left-hand side. So I'm going to draw you a couple of pictures, and I'm going to erase them as I draw them. So everybody just put a hold on drawing for just a second so you can see how this could look. The graph could look something like this. You definitely are going to have an open hole there because you can't, otherwise, you can't have a closed-in hole because you already got a closed-in hole. Otherwise, it wouldn't be a function. It wouldn't pass what was called the vertical line test, if you remember that piece of algebra. So you're definitely going to have an open hole. So let me draw that part in first. So maybe your graph looks like this. Maybe it looks like this. Maybe it looks like that. Your graph really can look anything like you want it to look like on the left-hand side. It doesn't even have to be smooth. It could look like something like that as long as it passes that vertical line test, and I don't think that one did. You can have all sorts of crazy stuff going on, okay? So draw the open circle at x equals 0, y equals 2, and then draw something on the left-hand side. I'll draw mine like this. The other piece of information says that on the right-hand side, right, the x approaches 0 from the right, so this piece of the graph, we're supposed to be getting close to a y value of 3. Okay, where's that going to be? Still on the y-axis, right? Just like the last one. But now we're up at 3 instead of at 2. So right here. So I have an open circle at 3 as well. And then I can draw anything I want, again, on the right-hand side of that. So I'll make a pretty sinusoidal kind of curve over here. We'll go like that. You can look anything like you want on the right-hand side as long as it gets close to that open circle along the y-axis at the y=3 location. Okay, so lots of different options on this. The parts that actually would have to look the same would be right here in the middle, agreed? Yep, everything else could look different. Any questions on that one? All right.